So, good morning, all of you. We have come a long way starting with the photoelectric effect, which substantiated the idea of Planck that electromagnetic radiation can be looked upon not only as a wave phenomenon but also as a quote unquote particle phenomena consisting of quantized packets of energy called photons. As I have told you, Planck himself did not particularly believe in the reality of photons. He thought it was only a kind of intermediate step or an effective language to describe what was happening during the interaction of radiation with matter. However, Einstein took this concept very seriously and he was able to explain all the great experiments of Hertz and Lenard and Millikan most importantly. Further experiments by Compton completely established that the photon picture is a perfectly valid picture even if it is in sort of disagreement or contradiction with the wave picture. And the next step came when Rutherford performed his experiments in order to determine the structure of the atom, and he gave the planetary model, the so called Rutherford model. We have discussed that at the great length. However, the planetary model gave rise to its own problems because the distribution of the electrons around the atom, if you imagine that there are orbits like that of planets, they were in highly discrete orbits, and in particular an atom in the ground state should not have been stable at all according to classical electromagnetic theory, because every accelerating charged particle should radiate. So, when it radiates it loses energy, and when it loses energy it starts falling into the nucleus. In particular, the most abundant atom that we have, hydrogen atom, should not be stable. In fact, it should not have lived or existed for more than 10 to the power of minus 9 or minus 8 seconds after it was formed. But we know that the universe is billions of years old, so that was a major problem. So, again we see that there is a tussle or a tension between the classical concepts and what experiments are revealing to us, very much like what happened in the case of the photon. And now the next thing that we studied was that it was the turn of Bohr, who again brought in the picture of photon and also the concept of quantization, not only in the energy of the electromagnetic radiation but also in the allowed orbits. So, once the Bohr model came, then a whole lot of things were understood, and in particular the discrete spectral lines were understood. The famous Lyman, Balmer, Paschen, Hund, all these series were understood. The mysterious constant, the Rydberg constant, was simply a combination of the fundamental constants or fundamental parameters, mass of the electron, charge of the electron, Planck constant and the speed of light. So, everything seems to fall in place. So, the next question that we have to ask, apart from other important questions, is what would the nucleus be made of? This is a very, very important question for us, because all that Rutherford scattering experiment revealed, it was elastic scattering, was that atom consists of mostly empty space. Electrons can be treated as sort of point particles, they are much, much smaller than the nucleus, and all the mass of the atom is constrained or contained in a very small volume inside the atom. So, let us start with that. So, to write a picture of the atom, so we have a nucleus, positive charge which is concentrated there, and then you have the electron orbits. We are drawing it in a plane, of course they are all in space, and Bohr quantization does not tell you in which plane my circular orbit is, it really is immaterial. Now, to give you a scale, what we are saying is that this length is of the order of 10 to the power of minus 8 centimeters or 0.1 nanometer, 0.01 nanometers, let us say. Whereas, if I were to magnify this, so I am magnifying this blot, this is of the order of 10 to the power of minus 15 meters. and this is of the order of 10 to the power of minus 10 meters. So, we are speaking of a factor of 10 to the power of 5 or 100,000 between the size of the atom and the size of the nucleus. We know that the nucleus contains positive charge for sure, because atoms are electrically neutral. Therefore, the big question is, what is it that the nucleus is made of, and if it consists entirely of positive charge, what is it that holds together? So, we have a number of questions to ask and to answer, and the answer to these questions will obviously come not from merely thinking or hypothesizing. We have to do an experiment. So, we have to sort of very, very carefully go through what is happening. So, mind you, we are in one shot migrating from a length scale of 10 to the power of minus 10 meters to 10 to the power of minus 15 meters. Therefore, you really need good delicate experiments in order to unravel what was happening. And it was really fortunate that in the beginning of the 20th century, not very, very beginning, because Chadwick's experiment were performed sometime in 1932, around that time we could actually get particles from radioactive decay which could probe the structure of the nucleus, not deeply but well enough to tell us what the constituents are. So, this lecture will start with a discussion of the constituents of the atomic nucleus, whatever is sitting at the center, and then we will try to argue out what they must be consisting of and what they should be. So, whatever I have told you so far, let me again quickly go through in a somewhat quantitative manner. So, the first recognition here for us is to realize, when we are looking at the fundamental structure of the matter that we have around us, we are looking at atoms and nuclei, is that there is this remarkable thing called charge quantization. There is no logical necessity for charge quantization, but nature does exhibit, and that is what you are seeing on your screen right now. So, what we are saying is that all electric charges come in integer multiples of a fundamental charge unit. That is the statement that we are making. So, let us denote it by modulus of E, because that fundamental charge unit can be either positive or negative. We know that there are two kinds of electric charges, positive charges and negative charges. Positive and negative attract each other, whereas like charges, negative and positive repel each other. And of course, the experiments involving the cathode rays and the anode rays, that is what they demonstrated. Cathode rays were positively charged, anode rays were negatively charged, and of course, you had the gamma rays which were neutral and which were later identified to be a part of electromagnetic spectrum. We have to remember this. So, when we say that there is a quantization, by that what we mean is that charge cannot, the value of charge or the magnitude of charge cannot vary continuously. It is not lying on a real number, but it can only take discrete values, and these discrete values are constrained to be integer multiples of this fundamental unit of charge. So, in this picture I have written Q equal to n mod E, that is what I have written there, Q equal to n mod E. N of course can be equal to 0, like in the case of a photon, if I look upon it as a particle. Then it can be plus minus 1, plus minus 2, so on and so forth. You will not find any evidence in any experiment for a fractional charge. Of course, this statement must be made with care, because we have some indirect evidence for what are called quarks. If we leave them out, then that is what we find. So, this was something demonstrated by experiments of Thomson and E by M, Millikan's experiment. So, to give you an example, electron has a value n equal to minus 1, because by convention we say that electron is negatively charged. Proton, which is 2000 times heavier. In fact, I should be very careful about this now. I should not use the word proton. I shall use the word the nucleus of the hydrogen atom. The nucleus of the hydrogen atom has a charge equal to plus 1. Therefore, you see the plus 1 and the minus 1 cancel each other exactly. That is what is happening, and therefore, the atom is overall electrically neutral. And if you go to other elements like helium, boron, beryllium, lithium, carbon, that is how the whole thing goes, nitrogen, oxygen, that is your periodic table, you keep on seeing an increase in the charge, number of charges that are sitting, number of electrons that are sitting in the atom, and a corresponding increase in the charge of the atomic nucleus, whatever its constituents are, and they are exactly cancelling each other. So you move along the row in the periodic table. I will show that to you in a minute. So that is what we have shown. There is a conventional notation called Z, and Z takes values 1, 2, 3, etc. Z does not take negative values, therefore the net charge in an atomic nucleus is always a positive integral multiple of the magnitude of the electric charge. That is the statement that we are making. Now, of course, we need an evidence for this statement that the charge of the atomic nucleus is exactly the same as the charge of the electron, but for a sign, and there is experimental evidence for that, and this figure is showing qualitatively, for example, what is the interaction potential between two atoms. So let us look at that. So what we have is, let us say, two hydrogen atoms. So this is a hydrogen atom, this is a hydrogen atom. So I can put a circle here, I can put a circle here. This is one hydrogen, this is one hydrogen. And we know hydrogen exists naturally not in its atomic state but in its molecular state. That is what we have. From your chemistry course, you have learnt a whole lot of it about how the orbits overlap, and then there is a binding energy associated with hydrogen atoms, so on and so forth. You have learnt a lot about the orbitals in your chemistry course. We will not get into that. The statement that we want to make is that even if there were a slight excess of charge between these two atoms, let us say this was positive, this would have been equally positive, the net force would have been repulsive and you would not have been able to form an atom at all. That is something very important for us. Unless we want to make a rather fantastic statement that one hydrogen atom has an excess of one kind of charge and another hydrogen atom has an excess of another kind of charge. For that there is no experimental evidence, so that is something that we have. So what we want to say is that this is strictly electrically neutral. And this is strictly electrically neutral. In fact, if you assume a circular orbit or a spherical distribution of charge around the proton, you can see that the net charge and the net dipole moment here is 0, the net charge and the net electric dipole moment here is equal to 0. Therefore, there should be no interaction at all unless they come very close, very close. Now, when you come very close, you can perform a very small calculation which is not difficult at all. Let me explain what you have to do. So you have the heavy nucleus here, you have the heavy nucleus here at a reasonable distance where they can actually interact with each other. And then I am going to write an exaggerated figure. I have an electron here and I have an electron orbit here, let us say. Now there is an electron sitting somewhere here, there is an electron sitting somewhere here. What you therefore do is to write down all possible potentials. So how many such terms are there? You have the repulsive term between the two nuclei. This is repulsive, so I will denote it as R. You can ignore them because they are very heavy, and in the equilibrium position, when the atom has been formed in the equilibrium position, you can take them to be completely stationary. You can ignore this particular term. Then you have the attractive term between the nucleus here and the electron here, which is responsible for the formation of the atom, and there is an attraction between the nucleus and the electron here, which is responsible for the atom. So this is corresponding to the atom. There is a repulsive term between the two electrons, so I will call it as an R prime. And then you have two attractive terms. and these two terms are what are responsible for the formation of the molecule. That is what we want to say. So there is a competition between the repulsive term between the two electrons and the attraction between electron of atom 1 with the nucleus of atom 2 and the electron of atom 2 with the nucleus of atom 1, let us say. So there should be a net attraction which should be able to give me the net force or the binding energy between the atoms. So what do? You know the radius of the atom, you fix the distance and you assume that it is in equilibrium and you slightly perturb, and if you make a binomial expansion, and sure enough you will see that there will be a quote unquote dipole term. So how is the argument that we are going to make? We are going to argue that when this electron comes very close to this, it distorts the orbit of the electron because of the repulsive power. My electron tends to go here. This electron tends to go here in a similar manner. So there is a dipole moment, and the two dipoles interact with each other. That is the picture that we have. And dipole-dipole interaction is always between two neutral entities because each dipole is electrically neutral. So please repeat this calculation. This is a favorite problem which will be given in all kinds of exams and interviews. So you will do well to work it out. If you did that, then what is going to happen is that you will see a picture like this. Very far away, you are not going to find any interaction between them at all. So at infinite distance, as always, I am assuming when the atoms are at rest, their total energy is equal to 0. So you see the potential is going to 0 very rapidly. As they come closer to each other, then there is an interaction potential between them, attractive potential. There is a small binding energy of a fraction of an electron volt, a very small energy. But if they come too close to each other, I am sorry about that, if they come too close to each other, you see they cannot sit on the top of each other. They are hardcore. The two electrons will start repelling each other like anything. There is also the Pauli exclusion principle, which you would have studied in your chemistry. So there is a strong repulsion. So the long and short of the story is that my distance between the atoms is somewhere here, and if you do a quantum mechanical calculation, it will tell you what the allowed energies are. So quantum mechanical or non-quantum mechanical, this is an example of, or in fact this is your famous van der Waals force, 1 over r to the power of 6 minus 1 over r to the power of 7. That is what you are seeing here. So this tells us that the atoms are completely neutral. Even a slight mismatch would have been given rise to problems. So in fact the current upper limits, if I remember correctly, are the ratio of the charge of the proton to the charge of the electron. If I look at this and I subtract 1 from this, and if I look at the modulus of this, this is less than something like 10 to the power of minus 22 or 10 to the power of minus 24. So the charge neutrality of the atoms is established to an enormous precision, up to 1 part in 10 to the power of 22. That is the statement that we are making. So this is a very important ingredient for us in order to understand the structure of the atomic nucleus. We should remember this. Without this, it would have been virtually impossible for us to argue what the nucleus should be composed of. Now this is not the only evidence for the neutrality of atoms. I am sorry, this should, the so-called equality of the proton and the electron charge, or for that matter any other quantization. So this is a picture from an accelerator where two protons at very, very high energy of the order of about 5 trillion electron volts, they have collided with each other. This picture is taken from the CMS collaboration. All of you must have heard of the discovery of God particle. This is the picture which gave rise, analysis of this picture which gave rise to the discovery of the God particle. God particle is electrically neutral, by the way. Here you see after the collision, thousands of particles are being produced. So protons will be produced, antiprotons will be produced, the so-called muons will be produced, all of them are charged, pi plus, pi minus, there are lots of charged particles will be produced. But all results are consistent with the fact that the total charge is conserved and all of them come in integer multiples of the basic electron charge. So what we are going to do is to take the electron charge to be a fundamental unit. So we say E equal to -1, and for a proton we are going to say charge is equal to +1, and henceforth we don't have to say my charge is this much in units of coulomb. Coulomb as a unit is only a matter of practical convenience, there is no significance for that, but really speaking I should define a coulomb to be the charge contained in so many electrons, 10 to the power of +19 or whatever. If it is 10 to the power of -19 coulombs, that is the way we should define, and this is what we mean by a natural unit. So we have got a very good evidence for the neutrality of the atoms and quantization. Okay. The next thing that we have to do is to look at the periodic table, which was given to us by the heroic work of basically chemists who studied chemical reactions. I am not showing you the full periodic table, but I am going to show you a section, and there are two numbers that you are going to see, which is important. I hope it is visible to everyone here. This is vanadium. So there is a number 23 and there is a number 50.9415. At this point, at this moment, please ignore all decimal points. Is that okay? So we are saying that it has a number 23 and there is a 50, and sure enough, if you count the number of electrons in vanadium, it is equal to 23. So by convention, the jargon is that its atomic number is 23. Now you can find out the mass of the vanadium atom. How do you do that? Make use of the Avogadro hypothesis. Take 1 mole of that and ask how many sitting of the 10 to the power of 23 molecules, whatever you are sitting there. So make use of that and determine the mass. So if you look at the mass of each of them, it turns out to be 50. That is what we have. So what is the statement that we are making? The statement that we are making is that the total number of electrons in vanadium is 23, which means there are 23 negative charges, which means there must be 23 positive charges to compensate for those 23 negative charges in the atomic nucleus. So, but the mass is 50. That is what we have. That means those 23 charges are distributed among these in this atomic nucleus, which has a mass of 50. Now, if you look at the hydrogen atom, for example, there is atomic nucleus which has exactly 1 unit of charge, which is compensating. So if I try to imagine that the atomic nucleus of any atom is built out of that 1 unit of charge, we get into trouble because I have a 50 units of proton mass. That is what I have, because, or the fundamental nuclear mass, because we know that the mass of the atomic nucleus for hydrogen atom is 2000 times greater than that of the electron. So when I am looking at the mass, I can completely forget the mass of the electrons. So this number at the bottom 50 is giving me the mass in the units of the nucleus of the hydrogen atom, and this is giving me the charge. So you go to chromium. So I have to go slowly. If you have to go to chromium, there is 24 and it increases by 1 unit. Then you go to 25, then you see it increases by 3 units, 50 to 54, so on and so forth, and it goes on and on. And the very interesting thing is that the rate at which the mass increases is not keeping pace with the rate at which the charge increases, but it is a slightly larger rate. You see that here. If you were to look at very slow, low mass atomic nuclei, that would have been different. For example, here it is 46 and 106, 78 becomes 195, 110 becomes 211. So in the whole region, actually, the mass in the atomic nucleus, the mass number in the atomic nucleus is roughly twice, and in fact it starts becoming more and more than 2. That is what we are saying. This is slightly more than 2 vanadium, but this is, on the other hand, it is 270 and 110. It is significantly more than 2. So in order to understand what the structure of the atomic nucleus is, that is what the constituents of the atomic nucleus are, we have to resolve the mystery of the mismatch between the charge and the mass. That is the statement that I have made, and we have to spend some time trying to understand that. So, these are the issues with the atomic nucleus, whatever I have described to you so far. So, the question that we are asking is, where does that extra mass come from? What holds the protons together, assuming that the nucleus is made up of the same fundamental atomic nucleus of hydrogen, which I shall call as a proton, which you saw in your cathode rays. So, what ultimately are the constituents of the nucleus? This is the question that we have to ask ourselves. Now, there are two possibilities. As of today, I know that there are two fundamental particles, electrons and protons, the nucleus of the hydrogen atom. So, I can be conservative and I can argue that the total number of electrons in an atom is not just confined to the electrons in the orbit. That is a statement that I can make. So, what I will do is I will say that the nucleus consists of a number of protons and a number of electrons. So, there are two kinds of electrons, rather electrons come in two ways in an atom. So, what we want to say is, this is the first picture. So, I want to imagine, let us say that this is my nucleus and this is my atom, the full thing. There are electrons sitting here. So, these I will call atomic electrons. And here I can say that what I have is protons, which is the nucleus of the hydrogen atom, plus nuclear electrons. So, that is the statement that I want to make. So, if I go back to this periodic table, so let me look at some random example. For instance, I can look at tungsten, W. So, how do we represent tungsten? I will write 74 W 183. So, what we say is that this is the number of electrons in the atomic orbit, and I will say there are 183 protons in the nucleus, plus 183 minus 74. So, that will be 13 minus 4 is 9, 109 plus 74, correct, electrons in the nucleus. So, if this picture is valid, it appears as if my nucleus hosts, supports, shelters more number of electrons than the atomic orbit. Now, this is a consistent picture as far as the charge counting is concerned. The other possibility that I have listed is that maybe there is a new electrically neutral particle, which is neither electron nor the proton or gamma or whatever. So, the decision between whether there are electrons in the nucleus or whether there are new kinds of particles can be taken only after looking at experimental details. So, we have to perform new experiments, and these new experiments were performed by first the Curie couple, Joliot-Curie and Marie Curie, and then it was followed by very, very careful analysis by Chadwick. That is what we are interested in. The first picture, namely that there are 109 electrons in the nucleus, is not probably all that far-fetched, because in radioactivity people had discovered there is something called a beta decay, beta minus decay, and you know that electrons can be emitted from inside the nucleus. Today we understand it as an emission decay of the neutron, and therefore, if somebody asserts that 109 probably it is true, except that it will give rise to greater complications, because there are also nuclei which will emit the antiparticle of the electron, namely the positron. So that means we will not be able to fix the number of electrons or positrons at all. So this is based on a primitive idea that that all these particles are there and they are coming out and they are not necessarily produced. But we should remember that this is not completely ruled out, because after all in beta minus decay my electrons are produced. That is something that we have to remember. Before we get into the details of the experiment, there is another complication, and this again we owe to the careful study of reaction rates by chemists. They are the people who gave us the periodic table. You have also isotopes corresponding to a given atom. So for example, in this periodic table I only showed you, for example, some iron or molybdenum or ruthenium or rhodium, so on and so forth. It is not as if there is only one species of each of these atoms. They can come in many species, avatars, so to say. For example, if you look at hydrogen, chemically there are 3 species of hydrogen. There are very small differences between them in their chemical reactions, but their masses are completely different. So we say there are 3 isotopes, and what are they? The corresponding atomic masses, is that okay? The bottom number are given by 1, 2 and 3. That is to say, all these 3 species of the hydrogen atom have only one orbital electron, and we know that orbital electrons are responsible for chemical reactions. The nucleus does not participate in chemical reactions, so they all have the same atomic number. That is what we have. They have a name: hydrogen, deuterium and tritium. That is the statement that we make. If you look at carbon, whose atomic number is 6, that is there are 6 orbital electrons, then it has again 3 isotopes. There could be even more, but they would be highly unstable: 12, 13 and 14. That is to say, the mass of the nucleus can be either 12 or 13 or 14. So we have to understand that. Then you have this great nucleus called polonium, which was discovered by Marie Curie in her studies on radioactivity. So when she had to give a name for this new element, she remembered her native country of her birth, the motherland. So she called it polonium in honor of Poland. That is what she did. This has 33 isotopes with the atomic mass ranging from 186 to 227. The stable one is probably around 200. The most stable is probably around 200 or 210 or some such thing. Never mind about that. So in proposing a model for the atomic nucleus, we should also be able to explain what is happening with these isotopes. Isotopes are a very important they are very important constituents of the periodic table, although they may not be shown in a standard periodic table because it is not easy to show them. Okay. So it is here that the experiments of Chadwick become very important. He was a student of Rutherford, and Rutherford had actually speculated that the nucleus consists of new kinds of neutral particles, and Rutherford went on to perform careful experiments. Not only did he perform careful experiments, he also went on to do a very careful analysis of his and other experiments to decide what the matter is. Okay. So the idea is to repeat the experiment of Rutherford, but then now you are not going to look at elastic scattering, but you look at inelastic scattering. So what we do is to look at elastic and inelastic scattering. So what would be an elastic scattering? What would be an inelastic scattering? So in an elastic scattering, for example, total kinetic energy will be conserved. All of you know it from your mechanics course, and total momentum is of course conserved. This is an example of elastic scattering. In the Rutherford experiment, you had the gold nucleus, you had your alpha particles and it was getting scattered like this. That is what was happening. If you ignore the recoil of the gold nucleus, because gold is very, very heavy, otherwise you can also take that into account, there is no problem about that. Then when I say that the scattering is elastic, we are asserting that the energy of the alpha particle remains constant throughout. So what are we saying? It started at infinity, it goes to infinity. So at t equal to minus infinity or at t equal to plus infinity, it is at a very, very large distance away from the nucleus. Therefore, there is no interaction between them. That means the incoming kinetic energy, E initial kinetic energy, is the same as E final kinetic energy, and we say this is elastic scattering. So what is happening in such a process is only a transfer of the momentum and not transfer of energy. That is a very important thing. Well, if energy is conserved, how is momentum getting transferred? The magnitude of the momentum is the same, but it is only the direction that is changing. So that is what we say. If I were to draw a line here, you see the momentum transferred. The scattering angle is somewhere sitting here. Is that okay? That is what we have. This is an example of an elastic scattering. I can also look at inelastic scattering. These experiments also you are familiar with, as we discussed that at some length in Frank Hertz experiment, for instance. What would be such an example? So let me give you a hypothetical case. I have an atom, let us say, and there is an electron sitting in the ground state. Now what happens? A photon comes, radiation comes. What it does is to give a part of the energy to the electron so that it can go to the first excited state. That is what is going to happen. And then the rest of it is going as a scattered radiation. Now you see, your energy, part of the energy is given to increase the internal energy of the atom. The atom is still at rest. Overall momentum is equal to 0, let us say. And then if you look at the final energy, there is not only a momentum transfer, there is also an energy transfer. Oh well, not only you can actually give an electron to send the electron to an excited state, you can actually ionize that. That is your photoelectric effect. So it will come out. So this is my photoelectron. So clearly here, if I look at the scattered photon, it will have a less energy. Whatever is given by the difference between the initial and the final, corresponding to the kinetic energy of the photoelectron plus this. So in all these cases, we say that the interaction is inelastic because the kinetic energy is not a conserved quantity. You have given it to internal energy or to eject or to break a system or whatever. So what Chadwick essentially did was to perform an experiment by bombarding light elements with alpha particles. Rutherford did an experiment with heavy particles, but Chadwick bombarded them with light elements. In fact, he went all the way from hydrogen to oxygen, if I remember correctly. It's one of the most beautiful experiments that were performed. The preliminary results, I think, were reported in Nature, and then he published a detailed paper in Proceedings of Royal Society. He was a British physicist. So what you do is that Curie had already discovered the radioactive properties of polonium, and polonium decays by emitting alpha particles. In fact, the dominant decay is alpha particle to start with, and at some point we will work out the charge mass balance. So as I told you, polonium has an atomic mass in the range of about 200. So this decays by emitting an alpha particle. All isotopes of polonium actually decay. They have different lifetimes. So you should be intelligent enough to use the right isotope, which has a small lifetime. That is what you do. And the energies range from something like 5.5 million electron volt to about 5.8, let us say 6 million electron volts. So these are good numbers. I would ask you to remember these numbers because we are going to use them later when we look at the binding energy of the nucleus. These numbers are interesting. So what Curie, Joliot-Curie and Marie Curie did for the first time and later by Chadwick was that to make use of these alpha particles of this energy and bombard light atoms. So we have gone all the way from hydrogen to oxygen, let us say. Oxygen has an atomic number of 8, if I remember. So that is what I have. So you have hydrogen, helium, boron, beryllium, lithium, carbon, nitrogen, oxygen. So these are the atoms that we have. He did very, very careful experiments and they studied what was happening as an end product. This is the experiment that they performed. So when you perform the experiment, what you do is to, in order to find out what the produced particles are, the first thing is that nucleus gets broken. So the most important experiment of Chadwick was on beryllium because it showed the most spectacular effect. So let us stick to beryllium for example. Soon after the scattering, beryllium itself ceased to exist. So we have come a long way. We started with the question whether atoms are unbreakable. They are infinitely hard, and now we have gone to the nucleus and we find that nuclei can also be broken. This of course is very, very important because we know that there is both spontaneous fission and artificial induced fission, and induced fission is what is responsible for our atomic reactors which produce whole lot of power and also the destructive weapons. There is also another process that takes place in fusion which we will study at a later time. So anyway, the beryllium gets broken and what comes out? So what are we saying? You want to know what is inside this ball, break the ball. You want to know what is inside the room, break the wall. That is the statement that we are making. So this was done by both the Curie couple and Mr. Chadwick. That is what we did. So when it happened, what happened was that when that scattering, new radiation was observed. Now I am deliberately using this word because today we preserve the word radiation for electromagnetic waves, but those days it was very difficult to distinguish what it was, whether it is an electromagnetic radiation or some other neutral particle. So anything that came out of a nucleus was called radiation. Alpha radiation, beta radiation, gamma radiation. So that was the word that was used. And this radiation consisted of two components. Charged and neutral. So how do you know that it consists of two components? The experiment is very simple. You, whatever is coming out, you apply a magnetic field. The charged fellows will all bend and go away. So let us say that there is, you have collimated the quote unquote radiation emitted from the disintegration of the beryllium nucleus, let us say. So this is a collimated. Then they enter a region of magnetic field, okay. Then the charged particles will start bending, let us say in this direction. If there are negative charge particles, they should probably bend in the other direction. Let us keep that also in mind. And then what I will do is I will make them interact with a gas. This is the typical setup of the experiment. Or it need not be a gas, it could be paraffin for example. It has to interact with matter, that is what you do. You can put your targets here also, no harm, so that I can understand the interaction with all the species, that is what you find. Sure enough, you found that there are a lot of them which are bending in one particular direction. So, no surprise about that. That means there are charged particles. And these charged particles, after bending, when they interact with matter, it could be either with a hydrogen atom or it could be with paraffin or whatever, they simply showed characteristics of interaction of cathode rays with matter, which were independently studied. So, what do? You ionize hydrogen atom, that is your fundamental atomic nucleus. Whatever you see the same thing happening here, except that your statistics has improved. Of course, the energies are different, that is what you have. So, you simply identify them with protons. So, no Nobel Prize for this, because the curvature, whether it bends this way or this way, because you know the velocity will give you the charge. In fact, you can find E by m, which will tell you what the masses of these quantities are. But then there are these neutral particles which are coming here, that is very, very important for us. How do you know that they exist? Because they don't respond to a magnetic field. What you do is, if you put again a paraffin target or hydrogen gas or whatever, these are found to have a great penetrating power and they can actually knock off lot of electrons. In fact, this neutral radiation can actually interact with the nucleus and further break them. So, this is the fundamental observation of the Curie couple, Joliot-Curie, Marie Curie, and also that of Chadwick. So, that is the statement that we are making. So, this slide essentially summarizes whatever I was describing to you all this time. So, what it says is that the bombarded nucleus gave rise to two kinds of species, protons and neutral radiation. Neutral radiation had enormous power, that is a very important thing for us. In fact, it was greater than the penetrating power of any known X-rays. X-rays were known to be the really most powerful radiation which you produced, so it was greater than that, and they could eject electrons and a number of protons. I am sorry, it is wrongly written here, from a number of hydrogen atoms. They could eject them. So, the question was, what was this neutral radiation made of? More remarkably, you find that there was no evidence for any negatively charged particle. So, my original hypothesis said that probably my atomic nucleus consists of what? Positively charged particles and negatively charged particles which compensate for the excessive positive charge, then they should have been bent here, and their E by m ratio should have corresponded to the E by m of the electron, because that is the hypothesis that we made. In fact, absolutely no evidence for found for that. So, you can simply junk the hypothesis that there are electrons sitting inside the nucleus, which is very good, because now we have to explain where these electrons came in the case of beta decay. But at least we do not have the embarrassment of trying to say that my nucleus consists of everything under the sun, proton, electrons, positrons, and I cannot fix the number. I do not have to worry about that. That is what we have, and this is what we have to fix. So, I have almost come to the fag end of my story today. How are we going to interpret this? Joliot-Curie and Marie Curie assumed that what was being emitted was photon. That is what they assumed, and there was already an evidence for photon matter scattering. I think I have discussed it earlier, but let me explain that to you again. So, soon after photoelectric effect, Compton discovered Compton effect. This is very, very important for us. And for the first time, Compton effect demonstrated that photons carry not only energy but also momentum. So, what is the experiment here? You assume that the electron is practically at rest and you send a radiation of frequency nu and you look at scattered radiation. You find that the scattered radiation has a frequency nu prime. This is the experimental finding, and you also look at the scattering angle theta. That is what I have. So, imagine there is a collimated beam of light which is coming, then there is an electron which is at rest. Now what I am saying is that I look at the angular distribution of the scattered radiation. So if I were to replace this picture by a particle picture, it's as if this electron, this radiation came and got scattered here. This fellow was initially at rest, but then it will get scattered and it will move in this direction. That is what happens, correct? Because total momentum and energy should be conserved. Now in order to understand this, Compton invoked the photon picture and he said that my energy of gamma is given by h nu and the photon momentum, the momentum of gamma is even given by h nu by c. That is what he said, and this is something that we have discussed at great length. Now you can imagine Compton scattering is elastic scattering between photons and electrons. So if my radiation is coming and going in the forward direction, then there is nothing that is happening. The maximum momentum will be transferred to this electron and therefore energy will be transferred to the electron at large angles. So all that you have to do is to write your momentum conservation equation for whatever particle that you wrote. Therefore that will give you a definite relation between the lambda of the scattered photon, which I will call lambda prime, and the angle at which my photon is scattered. That is your famous Compton formula, right? H by mc into 1 minus cos theta. That is the number that you are going to get. So Compton scattering had been very well established because we are speaking of experiments done in 1930, 1932. So taking a conservative approach, Marie Curie and Joliot-Curie assumed that the neutral radiation was nothing but the photons which are highly energetic. Now this gives rise to a number of problems because it will not explain to you the neutrality of the atom. They would have had to worry about that. But Chadwick, what he did was to perform a very careful analysis of these experiments. So for example, he looked at this neutral radiation which is coming. He looked at the scattering of this neutral radiation with nitrogen. He looked at the recoil momentum of the nitrogen nucleus. He did the momentum balance and he argued that the conservation laws, which are very basic to us, which are fundamental to us. What are the conservation laws? Energy conservation and momentum conservation. They are consistent if and only if we assume that the neutral radiation consists of electrically neutral massive particles. He showed if they are photons, they would be coming with an energy of 50 million electron volt and the energy conservation would go away. So to cut the story short, I am not going to do that analysis. With this very careful experiment, Chadwick concluded that there must be a new neutral particle which is roughly the same mass as that of a proton, so Mn, whose mass is 1.15 times the mass of the proton. That is what he gave with a 10% error. That is very important because you are writing 0.15, which is roughly 15%. So you are speaking, it could be very small also compared to the mass of the proton, whatever changes. And today the current value is mass of the neutron is 1.001 times the mass of the proton. Given the experimental situation and given the uncertainties and given the kind of statistics they were looking at, it is very clear to us that what Chadwick achieved was something very remarkable. Of course, subsequently its magnetic moment was discovered, so on and so forth. Therefore, now our task is to accept neutron as a new fundamental particle, a new particle which is a constituent of the nucleus. We can do away with the concept of electron in the nucleus and study the properties of atomic nucleus, which we will take up in the next lecture.